Asha, so we had done this exothermic endothermic, we had done all of that. Example of reactions, okay? Paired energy profile diagrams, and we did one formula, which was the main important thing, which was uh, every reaction there is bond breaking happening, and there is bond formation that's happening in every reaction. So it's the energy that is needed for bond breaking that's positive, and energy that is released during bond formation, which has a negative sign. So the overall energy enthalpy change would be this. Okay, that is what you're going to get. Okay, we were doing catalyst. So I'll just cover this very quickly. Okay, I told you that every reaction, initially you need energy to break bonds. Okay, right at the start, you need a lot of energy to break bonds. So what a catalyst does is that it reduces this activation energy. Or Kala explained how it happens. There's a type of catalyst which is homogeneous catalyst, and there's a type of catalyst which is known as heterogeneous catalyst. So I just gave you an example. Just for general knowledge, there would be very specific questions. You don't have to remember the equations. All you need to know is that maybe they would give you an equation, and you just have to use your common sense, like how does that catalyst work. So for example, we had this reaction, both ions were negatively charged, so they repelled each other, which made the reaction very difficult. So an alternate path is created. So that's one way of doing a reaction. You add a catalyst, and that catalyst creates an alternate path. You get the same exact products in that path as well. I'll give you one example of a heterogeneous catalyst. How does that work or reduce activation energy? So an example of a heterogeneous catalyst is that it has a different state. The Haber process is one example. Okay, what happens in the Haber process is that you've got nitrogen gas, and you've got H2 gas, and they react to form NH3. You got two molecules of NH3 gas. All of them are gases. But the catalyst in this case is a solid. The catalyst in this case is iron, and that Fe is a solid. So how does this heterogeneous catalyst work? So there's another way, which is called adsorption and deadsorption. So what happens is, the reason this reaction, so what's the reason why does this reaction have a very high activation energy? Why is it so slow? Kya reason hai?
Nitrogen is inert.
Okay, nitrogen triple bond is very strong. Okay. So the problem, I told you every reaction has a different reason why the reaction is not happening. So N triple bond N, it's a strong. So this one is a strong. So this one is a strong triple bond. Now, so if the catalyst would somehow make it easier to break the triple bond, that would speed up the reaction. So how can a catalyst make it easier to speed up the reaction? So what happens is, okay, transition metals are very good catalyst. So here's your iron Fe. Okay, let's say this is the surface of iron, and what happens is that this N triple bond N molecule along with the H2 molecule, they are flying around. They're gaseous, and both of them are flying around, and they would collide with the iron catalyst. So both the H2 molecule and N2 molecule are going to hit the iron catalyst. So why are transition metals good catalyst? So the reason for that is, So the reason for that is they've got more protons. Which is why they develop a slight tendency to attract electrons. Okay, so compared to normal metals, they've got more protons, so they have a very slight tendency. They don't gain electrons. Remember, they're metals. As an example, if I have calcium over here, potassium over here, potassium has 19 protons, right? It's in group 1. If I move across the period, transition metals are right in the middle. Iron has 26. So iron has 26 protons. And can somebody double check? Iron has 26. I'm pretty sure it's got 26. Nickel has 28. So then you've got, on the extreme right, you've got bromine, which has 35 protons. Okay, so the ones on the left, the reason why they're not good catalysts is because they like to lose electrons. Why do they lose electrons? Because the nucleus does not have a lot of protons, right? So they form positive ions. I said the ones on the extreme right, they've got too many protons in the nucleus. So the nucleus has a very strong positive charge. So they like to gain electrons. And they like to form negative ions, right? So when you move across the period, when you move across towards the right of the periodic table, there's going to be more attraction for electrons. And why do they have more attraction for electrons? Because there's more protons in the nucleus. Iba, clear? Is this clear? Is this part clear? Ahmed?
Yes, sir.
Yes, sir.
What this does is that, so coming back to this iron, why is iron a good catalyst, right? First thing is, there's a problem with the ones on the extreme ends. Again, I just told you the problem that they don't really like to gain electrons. They've got too few protons in the nucleus, and they like to gain electrons very strongly. Iron is kind of in the middle, very slight tendency to gain electrons. So why does that help you? Coming back to this, remember iron has this slight tendency to gain electrons. What it will do is, if the N2 molecule is close to the iron catalyst, what will happen is that the electrons in the triple bond will start getting attracted to the iron, not very strongly. Okay, we don't want them to be attracted too strongly. So the electrons in the bonds are going to be attracted towards iron. And that's known as adsorption. That there's going to be a very weak force of attraction. I said there's, let's go see. I said there's going to be a very weak force of attraction, and in this way, what happens is that the shared electrons would eventually, so there's one end, there's another end, and the shared electrons would eventually be pulled towards iron, not very strongly, just very, very weakly. The bond that's going to be formed between the nitrogen and the iron would be very, very weak. Because remember, iron likes to attract electrons, but very, very slightly. It's not like bromine that it likes to attract electrons very strongly. Same happens to this hydrogen as well. The shared electrons, they would eventually get attracted to, they're going to get eventually attracted to iron. Because that's, so that part is known as adsorption. So catalyst and reactant molecules, they form weak bonds. And in the next step, these weak bonds are going to break. Okay, remember the atoms and the molecules, they have some kinetic energy. They're flying around. So they're going to bounce back. Once they collide with the iron catalyst, they would eventually bounce back. So ये जो arrow होगा ना, that will because remember, they're not going to stick to it. It's a very weak force of attraction. So when they bounce back, these weak bonds are eventually going to break. And when they break, so all your atoms are now free to move around. Okay, the bonds have been broken. The atoms are now free to kind of move around anywhere they want. So the first part has been made easy. And that's known as deadsorption. So deadsorption is exactly the opposite, that the weak bonds between catalysts and reactants, they break. And this is how activation energy is reduced. This is how transition metals do it. Okay? The problem with bromine was that it would attract the electrons too strongly. It wouldn't let go of the nitrogen atoms, right? Okay, if it gets hold of, gets its hands on those electrons, it's going to keep those electrons. It's not going to give them back. The problem with potassium or group 1 metals is that they won't attract the electrons in the first place. Transition metals are the ones that have a very slight tendency to attract electrons. That's how they weaken the bonds. Okay, so imagine N2 and H2 molecules flying around, and when they hit the catalyst, the electrons, they get attracted to the catalyst. The shared electrons, they're gone. The bond between them breaks. When they bounce back, the atoms are now free to move around. Okay, Ahmed, Rafa, is this all clear?
Sir,
Yes.
the molecules are like nitrogen or hydrogen are going to be hitting the iron. The covalent bond is like going to break automatically or what?
It's going to break automatically. I mean, there's a reason for that. Okay, the iron is attracting those electrons in the triple bond. But if the N2 molecule comes close to the iron, right? What did I tell you about iron? It's got more protons, so it's got this greater attraction for electrons. Is that clear? So iron is doing the.
So the bonding pairs break and get attracted to iron.
So instead of the electrons being present in the middle, shared between the nitrogen atom, the electrons, they get attracted to iron over here. Clear?
And sir, what about the force of attraction that develops? What kind of force of attraction is that? Like intermolecular or electrostatic?
Chemistry, there's only one force of attraction, that's electrostatic. Okay? I mean, over here, what's happening is that what's happening is that you've got a nitrogen nucleus, right? 7 protons, right? You got another nitrogen nucleus which has 7 protons, right? And you have nitrogen's got a triple bond, so there's 6 electrons in the middle, right?
Yes, sir.
So that's all of that is negatively charged, right? So right now, this force of attraction is really strong. I mean, that's a covalent bond, right?
Yes, sir.
Okay. So the N2 molecule is intact. This nucleus of nitrogen atom, they're strongly attracted to the shared electrons. Okay? So that's why the triple bond is very strong. Here's what the catalyst does. When the catalyst comes in, now we've got iron and it's got 26 protons, right, in its nucleus. So what it will do is, iron and there's a lot of iron, right? There's another iron with 26 protons. There's another iron with 26 protons, right, in its nucleus. So what will happen is that these electrons will eventually get attracted to, but not very strongly, very slightly. So these electrons would eventually get attracted to, so instead of these electrons being present over there, these electrons are going to get pulled somewhere over here. Nitrogen and the catalyst will be fighting over those electrons, right?
Yes, sir.
So the triple bond has broken. Is that clear?
Yes, sir. And the electrons flow along with the atom, right? Yes, sir.
नहीं, the electron की क्या बात की थी?
Electrons वो atom के साथ ही जाते हैं ना?
हाँ, but let's say the electrons got attracted, so the electrons are over here. But this atom is not stationary, right? It's got, the force of attraction is not very strong that it's going to stick to it, right? So this atom has energy and it will eventually, like it came around, it bounced, it's going to bounce back, right? So when it bounces back, the attraction of iron was not that strong. Is that clear?
Yes.
But like bromine, if it had been 35 protons, then the attraction would have been very strong. And this nitrogen atom would not have been able to sort of fly off, right? But over here, the thing is that transition metals are good catalysts because they only attract electrons very weakly, not very strongly. Okay. At the end result is that the triple bond is gone, right?
Yes, sir.
So you just have to remember, keep it simple. You just have to remember that there is adsorption, that the reactant molecules, and it's not always that the whole bond breaks completely, right? Sometimes just a few electrons, they get attracted to iron. But even in that case, the bond has weakened, right? So the point is that the catalyst helps to weaken the bond. And you've got to remember adsorption and deadsorption. Okay. I said that's it. That's it about homogeneous and heterogeneous catalyst. Okay. So whenever from now on we study about catalysts, they're going to be, different catalysts have different paths. They work in different ways. These are not the only two ways. But एक तो ये charges वाला था, ठीक है, alternate paths being created, etc. So every catalyst, the only thing is that every catalyst, there's something that's preventing the reaction from happening, and the catalyst somehow helps to overcome that. Even in this case, why do transition metals act as good catalysts even in this case? Because the thing is that they have the ability to lose electrons as well as gain electrons. Like iron can turn into 2+, it can also turn back into 3+. For sodium, it's very difficult. For group 1 metals, it's very difficult. Like if it only loses electrons, it doesn't gain the electron back. For a non-metal, it's also difficult because if you have chlorine, then it will only gain electrons. It's not going to lose that electron back. So transition metals can do both things. Copper could be turned into a copper 2+ ion. The copper 2+ ion can easily turn back into a copper atom as well, copper metal as well. So even in these alternate paths, transition metals have this ability to gain and lose electrons. They can do both things. I said, but anyways, keep it simple. You won't be asked a detailed question on this. Just homogeneous, heterogeneous catalyst. Just a basic understanding of adsorption and deadsorption. Okay.
Okay.
So next one is, I said, now I'm going to move towards bond energy. Okay. And so first, the definition of bond energy. Now bond energy is that As a bond energy is that it's the energy that is needed to break a bond. So it's the energy that is required, needed to specifically break 1 mole of bonds. In gaseous in gaseous molecules. And 1 mole of bonds of the same type in gaseous molecules. I said one thing. If you look over here, bond energy is only defined for gaseous substances. TS only applies to or the values are defined for gases, not solids, not liquids. Or aqueous. Do you keep this in mind? Like if you're talking about water in liquid state and you're using bond energy, then you can't use it because it's not defined for liquid molecules. It's defined for gaseous molecules, and it's got to be 1 mole of bonds of the same type. Okay, so now the data booklet would be printed next to you, but I'm gonna open the old data booklet, okay, and we're gonna use this. Just remember the slight difference. Just remember this, that in past papers you were given a data booklet previously, but now the data booklet would be printed next to the question. So here's a table of bond energy. So if you're going to get a question, just remember, just type 9701 and you'll find the data booklet. Here, that's one part. So the stronger the bond is, the more energy that is needed to break that bond. There's another page, which is this one. ये दोनों अच्छा, this one, if you look at this, there are two types of bond energies. Okay, again, it's just explaining the two types. What happens is that there's a type called homonuclear. Don't get confused with these words. Okay, it's just that homonuclear is that it's a bond between the same type of atoms. So if the bond is between the same type of atoms, that's called a homonuclear. So hydrogen molecule, D is for deuterium. That's an isotope of hydrogen. You can just look it up. N2 molecule, that's a bond. So if you want to break a bond, a homonuclear molecule, this requires 944. Because remember, there would be other molecules which would not be homonuclear. They would be heteronuclear. For example, HCl, HBr, etc. They've got different atoms. There's a bond between different atoms, so that's the bond energy. And he's also stating that these are exact values. The reason these are exact values is because there's only one type of H2 molecule. That's it. And so that's why all of them are exactly identical. The thing is, then there would be some bond energies which would not be exact, but they would be just referred to as average values. Here, for example, there's a CH bond. Now, the CH bond could be of many types because there are many types of molecules that have CH bonds. Not all of them are exactly the same. Well, as an example, if you've got, if I've got a methanoic acid molecule, now you can see this one has a CH bond, right? And that CH bond is going to be different compared to this CH bond because the molecules are different, right? But both of them have CH bonds. This one has got a CH bond, this one has got a CH bond. If the molecule is different, the bond, there would be differences in the bond as well, right? Bonds, their electrons in the middle, they would change shape because of the other things that are attached to it. So the nuclear attraction between carbon and H would be different. I mean, things would be different between this CH bond and this CH bond. Is that idea clear? You clear, Saad, Rafid?
Yes, sir.
Yes.
So the point is that some bonds, the bond energy would just be referred to as average values. There wouldn't be exact values. Okay? You're going to take 410 for this one, you're going to take 410 for this one. But remember, this one is not going to be exactly 410. This one is not going to be exactly 410. Okay? So remember this. But H2 is always going to be 436. There's always only one type of molecule that's H2, that's it. उसी तरह बाकी सारे CC bond, right? There are many different molecules that have a carbon-carbon bond. Each one would have some slight differences. The electrons would not be shared in exactly the same way in all the, depending on the molecule, right? So, but don't get confused, right? It's just, don't get confused with this. Just keep it simple that if you have a carbon-carbon bond, you're going to take this value. If you've got a carbon double bond carbon, you take this value. Now, using this, I'm going to do the first question, which is based on, and remember, only for gaseous molecules. So we're going to do the first question, and I'm going to assume that all my substances are in gaseous state. So let's try this one. I've got N2 reacting with 3 H2s, and together they're going to form 2 NH3s, and all of them are gases. So starting with the first part, how do you calculate this? Enthalpy changes equal to bonds broken which is endo, minus bonds that are formed, and that's exothermic. So that's why you got a negative sign. As the way this is usually done is that one other way of writing this is bonds that are broken are usually in the reactants. So you break the reactant bonds, all of them, and bonds that are formed are in the products. So you form all the bonds that are present in the products, right? So how many bonds have you broken in this case? You've broken an N triple bond in, right? That's one of them, and then you've broken an H2 molecule as well. 3 of them. So one of this. And how many bonds are you forming? You're forming 2 NH3s. NH3 has 3 NH bonds. Two NH3s will have 6 of them. Okay, so that's the amount of bonds that are getting formed. And you have to be very careful about the sign. So this would be positive and this would be negative. And I'm going to pick the values from the table over here. So N triple bond N, what's N triple bond N? It's given over here. That's it's given as 944, right? And HH is 436. So I've got 944. You get positive plus 3 times. Be very careful with the sign. And the other values would be negative 6 NH bonds. So I'm going to take the NH bonds. NH would be, it's over here. That's 390 given over here. So we're going to use this. So it's 6 times 390. And you've already added a negative sign. So can anyone tell me what the answer is for this? What do we get for this?
Minus 88.
Minus 88.
Minus 88.
80?
88.
Minus 88.
As a kilojoules per mole, okay? Make sure you get the unit right. It's given over here. It's I mean, mostly it's going to be using kilojoules per mole. And so we're going to start with the first worksheet, which is. So all you have to understand in this is you have to figure out the number of bonds that are broken and the number of bonds that are going to be formed. So where's this bond energy worksheet? एक second. Just 1 second. So you're starting with the first one, right? So given this question that the bond energy of BRO is given, so forget the dot over here right now. So how many bonds are broken? You're breaking the first one. You're breaking an OH bond, right? And you're breaking an HBr bond. And how many bonds are getting formed? You're forming an HH bond. Okay, that's going to be exothermic. And you're forming a BRO bond. So this is broken and this is formed. What are the values for OH? That's if you look at the table, it's going to be 460. For HBr, I'm going to look it up. Not sure HBr compare. That's probably this one. For HBr, that's 366. For HH, that's I think that's 410, but we'll just have a look quickly. 436, sorry. So that's going to be minus 436. All of them. You have to be careful about the sign and you have to be careful about the moles as well. BRO, that's given, that's 235, minus 235. So Jaldi se batao, what's the value that you're getting for this?
155.
So we're getting plus 155, right?
Yes.
So we're getting minus bonds formed. Next one, OH, HBr, H2, and Br, right? So this one again, it's you're breaking for this one. You're breaking an OH bond, and you're breaking an HBr bond, right? So it's the exact same thing. So it's 460 and K366. And over here, you're forming water. That's two OH bonds getting formed. And no Br bond getting formed. Water has two OH bonds, remember that. Okay, so that's minus 2 into 460. So what value are you getting now?
Minus 94.
So minus 94. Okay, the last one, you're breaking an HBr bond. Okay, and you're forming an HH bond. Just one of them, right? So minus HH. So HBr kya tha? That's 366 plus 366. And HH is what's HH? That's minus 436, right? So what do we get?
Minus 70.
70.
Minus 70. That means 2 and 3 are correct. That they're both exothermic. The first one is wrong. As for the next one, similarly, you've got which stage in the free radical substitution of ethane by chlorine will have the lowest activation energy. So lowest activation energy, less bonds broken or more bonds broken?
Less bonds.
Okay, so less bond breaking happening. So ignore the dot. We'll explain that later, much later on. I said less bond breaking happening. So in which reaction do you think is the first reaction? You're breaking the bond, right? Cl-Cl bond. So energy would be needed for that. In this reaction, you're breaking a carbon-hydrogen bond. You have 2 carbons with 6 hydrogen. Now you've got 2 carbons with 5 hydrogen. So you clearly broke a bond, right? Over here, you're breaking the Cl-Cl bond, right? Because over here, there is no Cl-Cl bond. In the last one, you're not breaking any bonds. So the answer would be D. You clear? No bond breaking happening. Is that clear?
Yes, sir.
Yes, sir.
Achha, फिर next one ये कर लेते थे जैसे again bonds broken by its form. They've given the table. Achha, now the table would be printed similar to this. Okay. And again, most of these questions they didn't give you the table, but now it's going to be printed next to it like this. Achha, anyways, over here. So how many bonds broken? That's you're breaking one C triple bond C, right? And you're breaking 2 CH bonds. And 2.5 O double bond O. And remember, double bond is considered one thing. Okay? This is not 2 bonds. I mean, although it is a double bond, but it's considered one thing. Okay? But double bond, 496 for the double bond is for breaking the whole thing. How many bonds are formed? That's 2 OH bonds in water and 2 CO2s. CO2 में कितने bonds होते हैं? You need to know the structure. CO2 is this thing. So that's 2 CO2s, 4 C double bond O. Can you quickly tell me what the answer is for this? क्या होगा? C double bond C, that's 840. Then 2 times CS, that's 2 times 410. plus 2.5 times 496, I guess. 496. Not 496. What's 496? Then minus 2 times 460. And then minus 4 times C double bond O, that's 740. क्या बना इसका?
So I'm getting A.
A?
minus 980.
ठीक है, A. चलो ठीक है, इसको कंटिन्यू करते हैं कल. we'll try to do more questions on this. I'll share the worksheet with you as well. ठीक है?
Okay.
Okay, everyone.
Allah Hafiz.
That is